We present multi-level neural scene graphs for dynamic urban environments. This is a joint effort between ETH Zurich and Meta Reality Labs. Today, driving data is available at a truly unprecedented scale, which shows various great opportunities like building up-to-date digital twins of entire cities, but also poses unique challenges due to the limited scene coverage and the varying lighting, weather, season, and geometry across captures that make building photorealistic scene representations from this type of data extremely challenging. For example, on the right side, we see an example of a single intersection in Pittsburgh, Pennsylvania, covered by 20 different captures in Agobar's driving dataset. Fortunately, neural scene representations have made great strides in the last years, modeling both static and dynamic scenes. For dynamic scenes, the observations are usually represented by either a deformation of a canonical space or as point-by scene motion, for example, scene flow, and enforcing consistency through reprojection and depth losses. On the benchmarks that these approaches are trained on, this also works quite well. The problem is, though, that these are composed of data with teleporting cameras, having multiple viewpoints of the scene at the same time step, or quasi-static scenes, where the camera moves much faster than the scene itself, creating a similar effect to the teleporting cameras. This is, however, rarely the case when we deal with in-the-wild captures like street scene data, where we have fast object motion and limited viewpoint coverage. Therefore, methods for in-the-wild captures usually neglect the dynamics of a scene, modeling only static scene parts, yielding a good but incomplete reconstruction result. Few works have explicitly modeled dynamic scenes, and these works are either limited in terms of scalability or struggle with fast-moving dynamic object instances. Therefore, the goal of this work is to make dynamic radiance fields scale. To this end, we present a scalable, multi-level neural scene graph representation that scales to dynamic urban areas with more than 10,000 images and hundreds of fast-moving objects. To efficiently train and render this representation, we developed a fast composite ray sampling scheme. Finally, to test our model, we propose a benchmark for radiance field reconstruction of dynamic urban environments from heterogeneous vehicle captures. Let's take a closer look at this. Our proposed benchmark uses data from the Agobar's true vehicle fleet, which has geolocalized captures in several US cities in different weather, season, and time of day. It provides several calibrated and synchronized sensors, for instance, 7 global shutter cameras, a LiDAR, and a GPS. From this data, we select 2 geographic regions of interest with a total of 37 vehicle captures. Now let's formalize the task that we are interested in solving. We are given a set of sequences S with time steps t, ego vehicle poses PST, and calibrated cameras CS with extrinsics TC. Furthermore, for each object within a sequence, we are given its poses with respect to the ego vehicle, COT, and object dimensions, SO. Our goal is now to model the dynamic radiance field F theta that, given a location, a viewing direction, a time, and a sequence, predicts a volume density and a color. We model this function by first creating a scene graph with nodes V that hold latent codes for the specific geometry and appearance of each sequence or object, and furthermore, camera nodes. These nodes are connected by edges that represent rigid transformations between the coordinate frames of each node. Given our scene graph G, we use a static radiance field phi that represents the static scene, and a dynamic radiance field psi that represents the dynamic actors within the scene. To render our scene graph representation efficiently, we propose a ray sampling scheme where we first compute ray box intersections with a custom CUDA kernel, giving us entry and exit points for each ray box pair. Secondly, we perform a composite proposal sampling. The key idea is to estimate the density of all nodes along a ray jointly, using an efficient proposal network and the dynamic radiance field psi. After an initial uniform sampling, we perform importance sampling based on the joint PDF so that the further samples will concentrate at the first surface intersection. The implication of this is that only for rays falling into the line of sight of an object will we sample the more expensive radiance field psi more than a few times. Now let's look at the experiments. We show a comparison on a novel trajectory with the slow motion effect in the middle and see that our approach is able to faithfully represent both the static background as well as the dynamic foreground objects, while previous approaches struggle with both the background and especially with the dynamic objects present in the scene. Another nice property of our method is that we can change the sequence appearance and the object appearance will follow, meaning that there's an interaction between the latent codes in our multi-level graph structure. For example, if you focus on the white car on the right, you will see that the appearance of the car has changed significantly when exchanging the sequence latent code. In summary, we present a neural scene representation for dynamic urban environments that is scalable, can be trained on large-scale heterogeneous data, and allows for flexible de- and recomposition of both objects and scene conditions. Thank you for your attention.